Okay, so stats for this exam are up here and also posted on the key, which is up on the website now. Average was actually not too bad at all, given how alarmed some people sounded coming out of the exam. Average was actually 70.6, which means there's a 4.5 curve to get it up to the average of about 75, where I normally aim for. Standard deviation is higher than it was on the first two exams, which is pretty normal for OChem 1. Everyone starts out on more or less the same page, and then depending on how well people keep up with the material, it kind of spreads out the field over the semester. Someone got 107, awesome job. So it's definitely possible to nail the material. Okay, all right, so I think I'm going to just go through whichever parts of this people want to cover the most. All right, maybe just sort of a quick show. We can go through all of the problem numbers, and I can say like who wants to cover all or part of this one. So, okay, quick show of hands. Who wants to cover all or part of 1? Okay, a couple people. Who wants to cover all or part of 2? Like no one. That one was pretty easy. How about 3? A lot of people. Yeah, that's the hardest one. 4? Okay, a couple people. 5? Couple people. 6? That one was tricky too. And 7? Okay, cool. So I do this in order of most hands, and then we can work back to the ones that had fewer people who wanted to see it. So this will be a little bit out of order. All right, so let's do number 3. Okay, I actually more or less ripped this off from a textbook problem late in chapter 7. Only the one they had, I forget the number, but it was like, they did something like this, I think. And since I told you guys that you're not expected to be able to draw bicyclics, at least not like chair structures of bicyclics, I pretty much said, okay, we want it to be locked. So I think they gave you like the transdeclin, which is locked into that rotational, or into that conformation. And I said, I don't want to force you to draw that, so let's do something else that's also pretty effective at locking it in place, which is the Tert-Butyl group. Because if you remember, Tert-Butyl really, really wants to be equatorial, which means the other ring flip form is much less prevalent. Okay. So before we get there though, so how many degrees of unsaturation does the starting material have? So looking at the structure, remember that each degree of unsaturation is 1 ring or 1 pi bond. So we've got one of each. 1 ring and 1 pi bond is 2 degrees of unsaturation for the starting material. Okay, any questions about that? All right, cool. For B, how many degrees of unsaturation does the product have? We know that it's C12H21 OBr, which, as we covered in chapter 8, we can convert into C12H22O, because halogens and H's are equivalent as far as unsaturation. And then also oxygens we can just drop out of the formula entirely, so this is equivalent to C12H22. Something with 12 carbons, if it were saturated, it would have 26 H's, so we're missing 4, which means 2 degrees of unsat. Okay, so 2 and 2 are the answers there. Any questions about either of those? Okay, cool. So next up, we got to draw the chair forms of this molecule. Any, I guess, like rotational perspective on this that you showed was okay if it made sense. But the one that I have in the key is, I didn't leave myself much room there. Here we go. Okay, so one option is Tert-Butyl down, axial. The CH2OH group down equatorial, and then the double bonded group sort of neither axial nor equatorial. Or We could do Tert-Butyl Group down equatorial, the CH2OH group down axial, and the CH2 group, the double bonded group, sort of neither. Okay, any questions about that? Okay, quick side note that's worth mentioning, because I saw a surprising number of people do this. So this group, the CH2OH, is not the same thing as MEOH. Me specifically means methyl, which means CH3. Not CH2 with a couple bonds coming off of it. So I think people got dinged a small amount for doing that, but I just wanted to clear up the record on that first. Okay. Any questions about this one so far? Okay, cool. And then, so left or right, what's the more stable one? Right, because this group has the T-butyl, or this form has the T-butyl group equatorial, which we know is vastly more favored regardless of what else is going on, just because Tert-Butyl really wants to be equatorial. Okay. So, now that we've got the more stable one figured out, part D says starting with the more stable conformation of this molecule, so we're going to redraw that chair form down here. Just draw the mechanism and product for this reaction. Okay, so we've got Br2 around. We've got an alkene. This is actually just a mechanism out of chapter 5, but now we're including stereochemistry going on in here. So this is just alkene attacking bromine, bromine back attacks. And we weren't too picky on how you showed stereochemistry here because it could actually go either way at first during this step. But we know that only one bromine is going to get incorporated into the final product because there's only one Br in the formula. So this is where, rather than having the second Br come in and do anything, the OH has to sort of come in and do this. So this is actually just halo ether formation, just using like an intramolecular ROH group to close the ring up. Okay, so we end up with oxygen attached on here. And by the way, there's only one direction this oxygen can attack from, like under the ring, which means that it's going to end up in basically the down axial position, maybe skewed a little bit because it's also tied into a 5-membered ring, which means that this one, the remaining carbon, which now has the bromine on it, is going to be in up equatorial. Okay, so then the last thing we need to do is just deprotonate it. So okay, so I think as long as you showed the oxygen sort of closing a ring up under the molecule, we weren't super picky about like exactly the orbital or angular geometry there. Uh-huh.
Why is the OH favored over that second Br coming in? Is that just because the way the problem was set up and that was what was given?
Partially that, and also if you guys remember the proximity effect, like if the molecule can do something intramolecularly, it's usually going to be faster and easier than like bringing in some other thing to finish the job. Yeah, so that actually leads me into the part E of this problem, which is explain in under 30 words why this is the only product formed. I realized that this is actually a very vague wording of the question, and people actually had numerous different reasons here, so as long as you said something that was true and described something about this mechanism, then you probably got 5 out of 5. So if you said like the T-butyl group locks it axial into this, or locks it into this conformation, so the OH has to attack from underneath, that got you full points. If you said proximity effect means that OH is going to attack on this carbon because it's nearby and part of the molecule, that got you full points. Other levels of varying correctness that were sort of getting at one of those arguments got you some proportional amount of points. We pretty much just kind of eyeballed like this feels about half right or so. But yeah, if you said one of those things, it probably would have gotten marked correct if it matched what you had going on in your mechanism. Okay, so questions about any of that stuff so far? Okay, cool. I guess, yeah, so one thing you can use to like error check yourself on this is just the formula that you're given. Another thing is actually the degrees of unsaturation I put in there to sort of a little bit guide people towards the answer, because you know that if you got 2 degrees of unsaturation in the product, you must have, if you're getting rid of the pi bond, you got to form either a new pi bond or a new ring somewhere to keep the degrees of unsat at 2. So that's kind of what this ring closing is doing, is getting that degree of unsaturation back. Okay, so that's 3. All right, so I think the second most popular one that people wanted to go over was number 6. Let me move the camera real quick. Okay, maybe let's break this down into parts actually again. Okay, so going through A through G, how many people want to see A? Okay, cool. Okay, so A, what reagents do we need to make this happen? All right, so there's a couple of problems in the exam archive that are like this. It basically comes down to recognizing, okay, even though we normally have the alkyl halide before the arrow and then the base nucleophile on the arrow, it could just as easily be the other way around, just depending on which group we're emphasizing the importance of. And it might also help a lot if you remember that metal counterions can drop off because they're ionic bonded on there, which leaves us with something with an S- charge. So this is obviously not an alkyl halide of any sort that we can categorize, but it is a particular type of base nucleophile. So strong base or weak base? Yep, weak base. And good nucleophile, poor nucleophile? Good nucleophile, yeah. And so I guess actually that's not too important for subdividing it, but what we're trying to do is stick an extra 1 carbon on here, in other words a CH3. So really all we're trying to do is make a bond between the nucleophilic atom and a new carbon, which means that we just want to set up for SN2 with some kind of alkyl halide that has a 1 carbon alkyl group in it. So any sort of methyl with a halogen on it was fine here, like methyl iodide or methyl bromide. Okay. All right, any questions about that one? Okay, how about B? How many people want to see that? Okay, how about C? D? E? A couple of people for E. Okay. Okay, so you got bromine. And we're making a carbon-carbon double bond here. I sort of drew this in a different way than how it looks over here, but remember that we can freely rotate this thing. So this is completely equivalent to this, which might help see it a little bit more easily. Really, all we need to do is get the bromine and the H off and do an elimination. So I guess there's 2 ways to do that. One is with E2 and one is with E1. E1 is generally not the best choice because we know that it's pretty hard to get just E1 by itself. It's usually going to have at least a little SN1 mixed in there. You can tip the balance using heat a little bit, but probably if we can set it up so that we can get just E2 only, no other stuff mixed in there, that's probably going to be the better way to go. If you did set up for E1 and you want me to relook at it because it wasn't graded accordingly, then that would be worthy of a regrade, or at least bringing it in and showing it to me. Okay, but assuming that we recognize E2 is kind of the better choice here, so what kind of alkyl halide we got? Primary, secondary, tertiary? Secondary, right? So do we want I guess first of all, a strong base or a weak base if we're targeting E2 on secondary? Strong, right? And is good nucleophile or poor nucleophile going to work better for just E2? Poor nucleophile, yep. So we want a strong base and a poor nucleophile, which pretty much narrows us down to one main choice, which is what? Tert-butoxide, yep. A few people put LDA here, which is the other good choice. Good for you if you did that. But tert-butoxide is kind of like cheaper and easier to use, so that's kind of my default like representative of strong base poor nucleophile. Okay, so LDA is acceptable too though. Okay, so we got tert-butoxide here. This comes in, does E2 only, makes a double bond here, which if you rotate it around gives us this molecule. If you wanted, you could list more information like a counterion or a solvent, but this was like the bare minimum that you needed for this to work. Okay, any questions about that one? Okay, cool. So that was E. Who wants to see F? No? Okay, I think I saw a couple people. So F is actually just old school chemistry from, or relatively old school chemistry from the previous exam, just popping up again here. But this, going to this, all we're doing is adding a couple new hydrogens on here, which means that this is what reaction for alkenes? Hydrogenation, right? So you need H2 and either palladium on carbon or platinum on carbon. I guess if you're really thorough, I saw a few people that listed both. That would work, but why? So that was marked correct, but your lab director would probably like scold you for wasting money. Okay. So G, I think, was probably the toughest one on here. Yeah, so we'll definitely do that. Okay. Okay, so we've got an OH and a BR. And we want to make this molecule. Okay, so if we look at this, what we've actually done is having this oxygen here swing around, do an SN2 onto this carbon with the bromine. So this is actually an intramolecular SN2 reaction. So there's actually something pretty similar to this in the notes where, and in the exam archives, and I think I covered one example on Monday, but where you have like some long chain with an alkyl halide, you hit it with some base, it's just anything strong enough to deprotonate the OH group. And then this comes around, does SN2 onto its own tail, and you close a ring up that way. It also works for smaller rings. It's just not as favorable, but it's still SN2 happening here. So pretty much all you need is just some base that's strong enough to deprotonate the OH group pretty reliably. So really anything with a pKa greater than about, on the key I say 18, but you can actually get by with a little bit weaker than that just because the proximity effect is working to your advantage. So if you set anything down to like RO minus, it should have been marked correct, but stronger is better. Okay, if you had a base that was weaker than that, like say CN minus, which I saw a few people do, that's actually not strong enough to deprotonate this, so it won't allow SN2. Okay. So any questions about that one? Yeah.
So if I did like methoxide as my base?
Mm-hmm. Oh, yes, that should have been marked correct. So go ahead and submit that for a regrade. Yep. Yeah, sometimes like there's so many good valid answers for this one that a few might have slipped through the cracks. So definitely like let us know. Okay, so any other questions about part 6 here? Okay, cool. So I think I saw a bunch of hands on 7, is that correct? So, okay, let's do 7. Okay, so this one kind of put your octagon drawing abilities to work a bit. Okay, so I guess first of all, under these conditions, we've got what kind of alkyl halide for both of these? Primary, secondary, tertiary? Secondary, right? And what kind of base nucleophile? Yep, strong base and poor nucleophile. So for both of these setups, what kind of outcome am I predicting? E2, right? So a bunch of people, or at least a few people, tried to do SN2 and get the Tert-Butoxide onto the ring. That's not a very likely outcome. It's just too starkly hindered. Okay, so we're trying to do E2, which means we're going to form a double bond to one of the beta H's coming off of here, which means assuming we show both major and minor products, because we're talking about like multiple stuff forming here, our two products for this could look like potentially this or this. Okay, so based on what we know about double bond locations in bridged systems, one of those has a really big problem with it, which is that it's breaking what rule? Brett's rule, right? Yeah, because you can't have a double bond here. All right, so this one is ruled out, which leaves us with just one possible E2 product. Whereas down here, Brett's rule isn't tying our hands so much because the rings are big enough to accommodate a double bond there. The largest ring is 8 carbons or more. And you can make the other one as well. So it pretty much just comes down to if you picked correctly which one made 2 products and which one made 1, you got 5 points. And then the correct explanation, whether or not you actually use the phrase Brett's rule, or if you just said like, can't make a double bond here. I had one person draw this and write no in huge letters, which was pretty good. But yeah, that got you full points because just recognizing you can't make a double bond there is all you need. Okay, questions about that one? All right, cool. All right, so I guess out of the ones we haven't looked at yet, is there anything that anyone really wants to cover out of the remaining questions? Sorry, I see you first, and then you back there, and then you in the gray sweater. 5? Okay, I guess, how about yours? Number 1? Okay. Okay, okay, cool. So let's go through that, and then we'll do, which one's 5? Oh yeah, the E2 mechanism. Okay, cool, let's do both of those. Give me just a minute to erase the board, though. Okay, so number 1 here. Okay, so maybe let's do an example real quick. So if we hit this with, actually, I guess one thing to point out about this problem is a surprising number of people didn't remember the formulas for ozone or dimethyl sulfide. Definitely make sure you're comfortable with going from names to formulas on those. Okay, so hydroboration oxidation here. So this adds an H and an OH. Does it do it Markovnikov style or anti-Markovnikov style? Anti-Markovnikov, right? And does it do syn or anti-addition? Syn addition, yep. So what that means is we're going to add the OH to the less substituted carbon, and it's going to be pointing the same direction as the H that we put on the more substituted carbon. So that's one possibility. And this is the other. Okay. So, first thing we want to check between the two products that we just made is what's the relationship between them? Are these enantiomers, diastereomers, or identical? Diastereomers, right? Because all the stereochemistry out here on the bridge stays the same, but we're flipping some of the stereocenters out here on the right. So these are diastereomers. So, are they going to be produced in equal or unequal amounts? Unequal, right? Always, because they're different in energy. Okay, so you can pretty much just go through it and figure out what's the relationship between them. If they're diastereomers, it's always going to be unequal. If they're enantiomers, maybe equal, maybe not, depending on what kind of stuff you're given on the arrow. Question? No idea off the top of my head, to be honest. Yeah, we just know they're going to be different. Yeah. Okay. So, next one up. Actually, I guess quick show of hands. Out of B, C, and D that are left here, how many people want to see B? Okay, a few people. How about B? How about C? A couple people. D? Okay, a couple people. All right, so I'll do B, then C, and then how much time we got left? Oh, we got a while. Okay. Okay, so B was kind of the tricky one here, because I think a lot of people forgot about what ozinolysis does, even if they got the reagents right. Okay, so ozinolysis here. Remember that that's going to take an alkene and just cut it right across the middle and give you a couple CO double bonds. So you've got options on how to draw this. One is you can straight up just start out by redrawing the starting material with the double bond there, and then just get that double bond out of there and draw a couple double bond O's in where it used to be. And that's totally acceptable. Okay, if you want, you can also show the H explicitly, but you don't have to. Or you can redraw this as, if we fold all of the ring flat into the plane, which we can now do, you can redraw it as this instead, where both the carbonyl groups sort of fold back behind the plane. However you showed it, as long as you got the right connectivity and stereochem was good. Uh-huh. Because I guess it does say show stereochemistry explicitly. Yeah, sorry. Okay. So am I going to make any other products from this reaction? Right, I see people shaking their heads and those people are correct because there's pretty much only this coming out of it. I'm not having to worry about bold versus dashed because I'm not making any new stereocenters on this thing. So it's pretty much this is the only product, so I don't have to worry about equal versus unequal because that's it. Okay, any questions about that one? All right, cool. So let's do C. Okay, so Br2 MEOH. This one is actually pretty similar to A. The bridging part stays the same, and then you've just got a choice of like Br dashed and OME bold. Because remember, this is going to be an anti-addition where one new group is bold, one is dashed. Or the other way around could happen just as well. Or could also happen, I guess. We don't know how to tell which one's going to be more favored or less here. But we're going to get this one as well. Okay, so identical enantiomers or diastereomers? Diastereomers again. Which means automatically unequal. Okay. So any questions about those? All right, cool. So let's go on to D. So H2 and PD on C. Okay, so you can either show the H's explicitly or not here. If you do want to show the H's explicitly, you can say like bold H got added, bold H got added, which means dashed methyl, or dashed H, and bold methyl, because remember that hydrogenation like we're doing here is a syn addition. Both the new H's have to add on the same face, but it ends up not being super important because you have another H there anyway. So pretty much you can just like not bother even showing the H's and just say like methyl bold or methyl dashed there. So again, identical enantiomers, diastereomers. Diastereomers, which means equal or unequal. Unequal, yep. Okay. So I guess if you sort of take a step back and look at this problem, we're giving you a chiral molecule to start out with right off the bat. So it's pretty safe to assume that whatever you get, if there's more than one product, it's going to be unequal anyway. But just to confirm it, you can go through and check what your actual products are. Okay. So any more questions about number 1 there? Okay, cool. And so then the other one people wanted to look at in the few minutes I got left is number 5. So let's do that. Okay. So the easiest way to figure this one out, well, I guess first of all, let's work through this a little first. Okay. So H pH. Okay. Okay. So one thing I did screw up on this exam, and if this sort of caught you out, then that might be worth submitting for regrade, so let me know, is technically, so what kind of alkyl halide is this? Primary, secondary, tertiary? Secondary. If I'm shooting for E2, which, excuse me, which I kind of am with this setup, I should probably have given you a strong-based poor nucleophile like tert-butoxide. I sort of switched things around at the last minute and ended up giving you something that's not quite so clear-cut. So if you ended up interpreting this as E2 and SN2 happen or just SN2, let me know and we can look at that and you might deserve some points back. But let's just go through the answer that I was kind of visualizing when I put this together for the time being, which is E2. Okay. So, we are looking for the halogen here. I guess I could also have tipped the balance by adding high temperature onto the arrow. So we're looking for bromine. We're looking for a beta hydrogen there. And we want them to be antiplanar to each other. So the easiest way to show that is by just doing a Newman projection. So in the front carbon, if we're sighting down that bond there, we got H going up and right, methyl going up and left, and ethyl going straight down. And then in the back, we got bromine going straight up, H going down and right, and phenyl going down and left. A lot of people asked about what pH is during the exam. You don't need to know it to solve this problem, but just so it's on the record again. This is phenyl. It's just a benzene ring attached to whatever. Okay. So, we're trying to do an elimination. We need to get that group antiplanar to that group. So we can twist things around a little bit and say, okay, let's get maybe H down in the front, methyl, ethyl, and then bromine we can keep up in the back, and then H and pH. Okay, so now if we do E2, you're going to end up with the methyl and the ethyl coming off in front, and the H and the pH coming off in back. And specifically, you're making it so the ethyl group and the pH are pointing the same direction. So if we redraw that as an alkene, you should be getting H, pH, methyl, and ethyl like that. You can also figure this out without Newman projections, but honestly, I have a way easier time using the Newman projection to double check my work. So, okay. So other questions about that one? Yeah, actually model kits will also help figure this one out too, if you brought yours to the test. Okay, so that's it for 5. I think I'm going to wrap it up there. So if anyone else has any other questions about, how points were distributed, let me know. But otherwise, the exam regrade request is going to be obviously not next Wednesday because that's in the middle of fall break, but it'll be pushed back to Wednesday after we get back. Hey.
Did you see if this is the bromolecule?